And welcome to our EPA's monthly webinar series, Challenges and Treatment Solutions for Small Drinking Water and Wastewater Systems. Today's topic is Uranium Standards in Drinking Water and Removal Technologies Research at Small Community Water Systems. And as always, we offer continuing education contact hours for this webinar, and you can see the link there that you can send your email request to get full credit or to register for getting those CEUs. So as a disclaimer for these presentations, the information presented here has been reviewed and cleared for public dissemination according to EPA policy. However, mention of trade names or commercial products does not constitute EPA endorsement or recommendations for use. With regard to the CEU contact hours, you must be registered, as I previously mentioned. You must attend for 60 minutes, the entire hour, although we might have a few more minutes for questions at the end of those 60 minutes. Also, if you're in a room with others, the names of the people not logged in must be provided by the person who is, and you can send those names to the email address listed here. Unfortunately, certificates of completion cannot be given at this time for webinar recordings, but only for this live webinar at this time, although
so if you miss,
I'm sorry, if you've missed the, I'm sorry, we're getting a little bit of feedback here. If you've missed the poll question, there we go. I'm sorry about that. If we missed the poll question, or if you have greater than 5 people in your room, please go to the questions box on your little dialog box in the upper right and indicate how many people are in the room with you. That would help us quantify how valuable these webinars are, and that we can get that to the people. So, and also a final note is that the slides are available in the handouts for this presentation. Okay, so I think that covers it with regard to CEUs. The first presentation is by Samuel Hernandez. Samuel is an environmental engineer in the Office of Groundwater and Drinking Water. He currently serves as the Drinking Water Radionuclides Rule Manager, handling all aspects of the radionuclide rule, including responding to inquiries about the principles and the applicability of the rule, as well as providing support to states and to other EPA offices regarding the technical basis of the rule. Prior to joining EPA, Sam worked at the U.S. Nuclear Regulatory Commission as an environmental project manager. Sam has a BS in chemical engineering from the University of Puerto Rico and a master's degree in environmental engineering from the University of Maryland. So at this time, I'll gladly hand this off to Samuel Hernandez in Washington.
And Sam, you may be muted. Sam, can you unmute your phone line?
Can you hear me now?
Yes, we can hear you.
Okay, good. So I'll start again. Yes, I'm Sam Hernandez. I'm with the Office of Groundwater and Drinking Water here at EPA headquarters in Washington, D.C. So today I wanted to talk a little bit about the drinking water standard for uranium. So I'll just go and provide a quick overview of requirements of the Safe Drinking Water Act. I want to talk a little bit about health effects of radionuclides, specifically for uranium, some of the rule requirements in addition to monitoring requirements, and also provide some examples about how we determine compliance, for initial monitoring and also compliance and violations. So just as a background, CIDWA mandates that EPA set standards for drinking water to protect the public against health risks. And those standards, we promulgate MCLs, which are maximum contaminant levels in drinking water. In addition to MCLs, as part of the rulemaking process, we also establish MCLGs. And our regulations apply to community water systems. So since we're talking specifically about radionuclides, just some of the sources where we might get radionuclides in drinking water. In the case of uranium, we're concerned with naturally occurring radionuclides. Now, the concentration of these will depend where the source water is located, so it varies by region, and also depending if it's groundwater from the geological formations. The radionuclide rules we also include in our standards man-made radionuclides. That's more specifically the beta and photon emitters. And some of the sources of that would be from nuclear power plants or hospital activities, medical facilities, and industry. I also wanted to make a distinction here because while we talk about uranium being a naturally occurring radionuclide, some man activities might result in the accumulation of uranium. But I just wanted to mention that because it's not specifically man-made, but due to man activities, it might be concentrated. So the types of radiation, we're mostly concerned with ionizing radiation. I have here examples: alpha radiation, that would include uranium, beta radiation, and gamma radiation. All of these are regulated in the radionuclide rule. So the way this will work, an example here for uranium, the isotope will decay. It will convert to another form of isotope, and it will emit radiation. In this case, you see that alpha radiation. And depending on the radiation you're talking about, it has different energy. So the alpha, it's stopped by a sheet of paper, you could stop alpha radiation. And then beta and gamma have more energy, so they could go through skin, and in this case, wood. So you might ask, why are we regulating alpha if a piece of paper could stop it? Well, the reason is if it's in drinking water, and you drink water with alpha in it, it's already in you, and it could have significant health effects. So the health effects for radiation, ionizing radiation has could cause damage to living tissue. It increases the likelihood of cancer. In that case would be additional cases of cancer. You also have the risk of congenital defects. And then for the case of uranium, it has ionizing radiation that can damage tissue. We're mostly concerned with kidney toxicity associated with uranium. So these health effects, the ones for the ionizing radiation, what we are concerned is that this energy could have the ability to affect DNA and cause damage to DNA. So one of the issues with this is that mostly for children and infants, since they are developing and replicating DNA so quickly, sometimes if you have damage to DNA and the DNA is replicating quickly, it doesn't have enough time to regenerate itself. So when you have a DNA that has damage and it replicates or duplicates, that damage is carried on to the next replication of the DNA. So that's the biggest concern that we have. In most cases, you could have some damage, but then that damage could be repaired in time for the next time the DNA is duplicated. So one of the issues, as I think it's explained here, if you have a error in that DNA coding, and it duplicates, then that error gets propagated. So that's where the issue with tumors comes in and increased likelihood of additional cancer cases. So in the specific case of uranium, there's three main isotopes that occur most abundantly. They emit alpha radiation, and while the information I just provided about the ionizing effect of alpha is true, in uranium we're mostly concerned about limiting its toxic effect as a heavy metal on the kidney. So that's how we base the MCL for uranium. Now, I wanted to add something in addition to that. In the case of uranium, it's something that's very interesting about this one is that when we set the initial MCL, which is based on feasibility of a system being able to remove uranium from drinking water, we established that feasible level was at 20 micrograms per liter. But as EPA was going through the rulemaking process and we did the economic analysis, we found that at 20 micrograms per liter, the benefits afforded by that were not justified. The cost did not justify the benefits. So for that rulemaking, administrator used one of the authorities that the administrator has to set the MCL at a level that might be higher than the feasible level, but which is a level that the cost justify the benefits. So the rule requirements, it became effective from 2003, applies to community water system, and the MCL for uranium was set at 30 micrograms per liter. Some of the other requirements from that rule, we had an interim regulation dating from 1976 for radium, for radium-226, radium-228, a gross alpha and beta particle. So those three regulations became final in 2003. Now the rule required monitoring at all entry points to the distribution system. Here it's a brief comparison between the 1976 rule and the final rule that was promulgated in 2000. In the case of uranium, we didn't have a MCL in the 1976 rule, and in the 2000 rule it was included as that 30 microgram per liter MCL. For uranium, the MCLG, that's the goal which we assume where we won't see any health effects. That's 0, and the health effects, again, kidney toxicity and bladder cancer. I also listed here the other radionuclides rule, just for your information there. Here I included some information about the monitoring requirements. Now you will see that these dates are way back when the rule was originally promulgated, and that all systems had to conduct initial monitoring at every entry point to the distribution system. Now I include this information here because even though these initial monitoring requirements had to be completed for a number of years now, these requirements also apply to any new system or any system that it's using a different source water, or that the composition of the water would change and the state determines that to meet these conditions they have to conduct initial monitoring again. So again, it's based on quarterly samples at entry points, and each entry point to the distribution system. As part of that initial monitoring, that will determine the subsequent monitoring scheme, and there's different tier levels in that would result in systems having to monitor either every 3 years or once every 9 years. And if a system, once they complete initial monitoring, it's still above the MCL, then they have to conduct quarterly samples until the system is in compliance. So again, this is just some of the information just provided. States have some latitude and authorizations to waive last 2 quarters of initial monitoring, and this compliance is based on running annual average. Again, here, something that's important is that the monitoring has to be conducted at every entry point to the distribution system, and these will be points that are representative of all the sources being put into the distribution system. So based on that initial monitoring, as I previously said, system could be afforded to have low reduced monitoring, and we have a very specific set of conditions for that. That would be if system is below the detection level, then the next sample or the monitoring event would be every 9 years. There's another condition for 6 years. It's between the detection level and half of the MCL. 3 years, it's 1/2 of the MCL and below the MCL. And then if it's in a violation, then quarterly samples must be conducted.
That's not very frequent.
It's the same table, just to illustrate different options you had. I included here an example of how you would determine that running annual average to determine the monitoring requirements. So in this example, there were 4 samples taken, 16, 25, 15, and 20. The way you would do the running annual average, sum those divided by 4, you get 19. So in this case, this system is below the MCL, and the standardized monitoring framework will call this system to monitor again in 3 years. Now, I included here some information about gross alpha, because the rule allows systems to use the results of gross alpha to determine compliance with uranium. Now, there is some specific conditions that have to be met, and for example, if a system gets results that are below 15 picocures per liter, they could assume that all the gross alpha is uranium, so they could substitute that requirement. If it's above, then uranium sampling must be conducted. Here's some information about how to do those calculations. Again, you would have to, this is in the case that you're calculating net alpha, and there's some requirements to do that. Just included here some of the information about how you would convert mass of uranium to activity, and also how you would convert uranium activity to mass. And again, this is helpful in determining compliance with the alpha requirement. Increased monitoring, as I mentioned previously, if the initial monitoring result is that the result is above the MCL, then quarterly samples must be conducted until 4 consecutive samples are below the MCL. In here, I included a few examples of determining evaluations with uranium. Now, in this example, I'm assuming that the state determines that the compliance monitoring scheme will call the system to collect 4 quarterly samples. Again, once the system it's done with its initial monitoring, the state might decide how the subsequent monitoring requirements are to be conducted. But it's very possible that, for example, a system did initial monitoring and the result was that the system had to monitor again in 6 years. The state could very well ask that system to do just 1 sampling event at every entry point for that system. In here, I'm including some examples that would say that the state require 4 quarterly samples. So in the first example, we get that result of 140 micrograms per liter. Then that would be more than 4 times the MCL. Next example, the last result will cause the running annual average to exceed the MCL, and then the last example, it's that the running annual average it's above the MCL. So these are just some quick examples to try to show how you would calculate that running annual average. And in this case, all of them result in violations. So that's all I had for the uranium presentation and the requirements for the drinking water standard. I'm guessing that we're going to go to Tom now.
Okay, and ORD, it sounds like your phone line is also muted.
Go ahead.
Hello?
Okay, we can hear you now.
Oh, heavens, the light was green. However, I will double back then. Thanks, Samuel, for your presentation. We'll handle all questions at the end of Tom Sorg's talk for both speakers. If you've missed it, if you missed the poll, you please go to the question box and insert how many people are in your room, and that will be helpful to us for documenting how well this webinar series is done. So, to introduce Tom Sorg, Tom has over 51 years of experience with federal environmental programs. His experience includes the past 42 years with the Drinking Water Research and Development Program at EPA, and 25 years as the chief of the Inorganics and Particulate Control branch of the Drinking Water Research Division. Tom's research emphasis has been on drinking water treatment technologies for the removal of inorganic and radionuclide contaminants from water supplies, including the removal of arsenic. During the past 12 years, his research focused mainly on treatment technologies to remove arsenic from drinking water. This effort included his oversight of the U.S. EPA arsenic removal full-scale demonstration program. And with that, I will hand it off to Tom for his presentation.
Thank you, Tom. This is Tom Sorg, and welcome everyone, either a good morning or an afternoon, depending on where you're located. A year ago, I gave the first webinar, Small Systems webinar on arsenic. And there are some similarities between arsenic and uranium. Both of them are anions, and as a result, the treatment technology for each one is very similar. Today I'm going to break my presentation down into 3 parts. I have a few slides on uranium chemistry, and then I'll talk about treatment technology, and then finally some comments on the disposal of waste, which is always a concern with most small systems because of the nature of uranium being a radioactive contaminant. As I said, I have a few slides on the chemistry, going all the way back to your first grade chemistry. You're aware that not all atoms are stable, and each isotope has its own decay rate. And there are 3 decay processes, and these were mentioned by Sam in his presentation. We have alpha, beta, and gamma decay. The alpha particle is a helium nucleus, a very heavy particle compared to electron, and then gamma rays, the high energy gamma rays. And we also talk about half-lives, and that means 1/2 of the atoms that will decay. A similar slide to this one was shown by Sam, and the reason I brought this in is particularly to note that, as we'll see and has already been mentioned, that uranium decays mainly as an alpha particle, which generally can't even go through paper. And one of the questions that comes up occasionally is if you have, let's say, an ion exchange system, you're removing uranium, your operator, is there any concern about exposure of the radiation coming from the system? With an alpha emitter, you can't go through paper. Certainly it's not going to go through a steel or fiberglass tank or the water that's in the tank itself. There are 3 decay series, uranium, thorium, and actinium. The 3 uranium isotopes come from the uranium series and the actinium series. In this next slide, I show the uranium series. It starts out with U-238, eventually gets to U-235, and in the same series it produces radium-226 and also radon-222. It generally ends up being the solid element Red-210. These are the 3 uranium isotopes. As I said, uranium-238, 234 come from the uranium series and 235 from the actinium series. All 3 of them are alpha emitters, and all of them have extremely high half-lives. And this is a comparison of the half-lives of uranium to radium 226, radium-228, and radon-222. As you can see, uranium has an extremely long half-life as compared to the other radionuclides that we regulate. In terms of the chemical concentration, we find uranium in the microgram per liter range, similar to arsenic, much lower than if you find calcium, magnesium, or iron, other natural elements in groundwater, and much higher concentrations as compared to radium. As already been mentioned, the uranium MCl is 30 micrograms per liter. This radium MCl is a weight unit. It's not a rad unit like radium or gross alpha, gross beta. And as already been mentioned by Sam, you can do some conversion. That last line at the bottom shows the conversion of 0.67 picocuries per microgram of uranium, or 30 micrograms equals 20 picocuries per liter. And this assumes that the occurrence of 238, 235, and 234 occurs generally as found in the environment. And as shown here, 238 is 99%, and 235 and 234 very small percentages. Now, if these concentrations change, then that conversion factor would change. But for the most part, if you go through the literature, you'll see this conversion number of 0.67 picocuries per microgram. Of the chemistry slides, this is probably the most important one. Uranium has 4 oxidation states, with 4 and 6 being the most common oxidation states found in the environment. It's a very active element. It reacts with water in the environment to form uranium oxide, and this species will react with a number of other natural occurring contaminants in water, particularly carbonate. And as you can see in this species diagram, you can experience either a cation a neutral species or an anion species. I've listed the anion species in red because in natural waters normally the pH runs from 7 to 10. So what we find in groundwaters is that the uranium usually occurs as an anion, either a -2 or a -4. Okay, I'm going to move on to treatment technology. In all of our regulations, we identify what we call best available technologies, and these usually applies to large systems rather than the small systems. Back in, or I guess about 20 years ago when they modified the Safe Drinking Water Act, the act required that we identify small systems compliance technology. As you can see in this slide here, there are 4 technologies listed at BAT, but 6 for small systems compliance technology. All of them very effective for the removal of uranium, anywhere from 80 to 99%. Line softening and coagulation filtration are usually used by large systems and on occasion by small systems, but not that frequent. And as a result, my further comments are going to be limited to ion exchange, reverse osmosis, a few comments on activated alumina, and then finally point of use RO. This slide shows the selectivity series for anion treatment. Dennis Clifford, who has written a chapter on ion exchange and absorptive media in the AWWA Handbook, Water Quality and Treatment, shows the selectivity series. And as you can see, at the high end of the series, uranium is number 1. It's the most preferred anion. Sulfate is second, and it will impact the performance of these systems for removing uranium. The more sulfate you find, the less removal capacities these resins will have. As indicated here, we've seen these anion resins move up to remove up to 400,000 bed volumes. Arsenic is the 3rd one in line. It generally breaks through right before sulfate. And then nitrate is number 4, and then bicarbonate. A comment about bicarbonate. It usually is removed in the very early stages of the breakthrough curve. The pH will drop to 5.5 to 6, and then it slowly rises to the inlet pH during this period of removal. The concern here is that it produces low pH and alkalinity water during the first few hundred bed volumes, which could be a potential problem with corrosion issues. This can usually be handled by 1 of 2 ways. If you have 2 tanks in parallel, you can stagger, this has to do with anion exchange treatment, but you can stagger the way they are removing uranium. If you're using it on a regenerated basis, you can stagger them such that when one tank is producing a low pH alkalinity water, it's then blended with the water from the second tank that is further beyond its removal of bicarbonate. Or you can put the water into a storage tank, where blending goes on. In terms of operation, the conventional anion resins are usually operated with an empty bed contact time of about 1.5 minutes or higher. My experience has shown that most systems will operate between maybe 2 and 3.5 minutes of empty bed contact time. You can operate these systems 1 of 2 ways. You can regenerate them with salt. 2 to 3 bed volumes of concentrated salt will do a very good job of regenerating an anion exchange system being used for uranium removal. Or they do not have to be regenerated because they have such a large capacity. Many of them are used on a one-time use basis or on a throwaway basis. Back in the year, I think it was 2008, Jerry Lowry, who I've known for a long time, and Jerry's done a lot of work with technology for the removal of uranium and radium and other radionuclides, gave a presentation at our small system seminar here in Cincinnati, as I said, in the year 2008. And I've borrowed a few slides from his presentation on rad removal. And so I want to give him credit for a few of these slides I'm going to show. This is a schematic of common or typical anion removal treatment system, 2 tanks in parallel with a salt tank for regeneration. And this is one of the systems. As you can see, the 2 tanks, and then in the right-hand corner, the tank that's holding the brine waste for regeneration. I pulled out and are using 2 of the slides that he used to talk about the performance of these systems. This is a system that he installed in a New Hampshire water supply, treats 50 gallons a minute. The uranium concentration is around 34 micrograms per liter. Sulfate, moderate level, around 23 milligrams per liter, pH 7.25. This tank holds 15 cubic feet. He operated it at 2.2 minutes, and he had a service cycle reported at around 100,000 bed volumes, which translates into operation of 273 days. At that point in time, you then could regenerate it, or you could actually use this one on a throwaway basis. Second system, I again using from Jerry's slides, is a system he installed down in North Carolina. This is a slightly different design system and has, as you can see in the slide, 6 small tanks of media or of resin. The system itself will treat 110 gallons a minute. The uranium concentration is around 23 picocuries per liter, which is above the 30 micrograms per liter. Sulfate very, very low, iron very low, so there's no issues with iron fouling. pH around 7.8. The total resin used in these 6 containers is 14.7 cubic feet. And he operates these at a 1-minute empty bed contact time. He found a service cycle of 400,000 bed volumes, and so these systems could last up to almost 5 years, and he reported an operational cost of $1,900. In a case like this, if you're operating the system for 4.5 years or 400,000 bed volumes, you're not going to regenerate them. You're going to use these on a throwaway basis. I have found that the resin costs so much more than the tank that in a situation like this, rather than removing the resin and replacing it, in almost all cases, small systems like this will just take the entire tank out with the resin and dispose of the tank and the resin and put in a new tank with fresh resin. Now I'm going to switch over to a couple of systems that we had in the arsenic demonstration program. And in these 2 systems, we had a combination of both arsenic and uranium. This first one is a California system. It has 2 tanks. You can see the 1 tank, but behind it is the 2nd tank. Each tank can serve or treat 50 gallons a minute. The arsenic concentration was 35 micrograms per liter, the uranium 34 micrograms per liter, both over the MCL. Each tank of media contained 27 cubic foot, of this case, a media called Arsenex NP, and this is a modified anion resin. So it's an anion resin, which is good for uranium removal and arsenic removal, but it was also modified for iron, and it was modified for iron for increased performance for arsenic removal. System is operated with a 4-minute empty bed contact time. The pH is 7.0, sulfate 36. The next few slides I have show the performance of this system. This system was monitored for 8 to 10 months. I might go back and say the 2 tanks, they operated 1 tank at a time with the second one as a backup tank, that one that they had to close down the first tank due to breakthrough, then they would flip over to the 2nd tank. So this is the breakthrough curve of one of these tanks. And as you can see in this slide, the arsenic in the influent water is around 40 micrograms per liter. if you look at the breakthrough curve down here at the bottom in green, you can see the arsenic began to break through around 20,000 bed volumes and achieve a total breakthrough at the MCL of 10, just short of 35,000 bed volumes. This is the breakthrough curve for uranium. The uranium was just slightly above the 30 microgram per liter MCL. And as you can see through the 35,000 or close to 35,000 bed volumes where we achieve arsenic breakthrough, the arsenic or the uranium was taken all the way down to detectable limit, which was right around 1 microgram per liter. So this system had to be closed down, not because of the uranium. It still had plenty of capacity for uranium, but it was closed down because of the arsenic. A few comments about activated alumina treatment. It's listed as the small systems compliance technology, and in the chapter written by Dennis Clifford in the AWWA handbook on water quality and treatment, he shows this selectivity sequence. And as you can see, uranium is not listed. And I've been able to find anywhere in the literature where anyone's done work to show the exact position of uranium. But based upon work that we did many years ago and also by the University of Houston, I would suspect it's down the line or in the middle of this selectivity sequence. The work we did back in 1980, in the 1980s, we brought water up to our facility here in Cincinnati from some Florida groundwaters. The uranium concentration was ranged between 273 and 432. We ran several tests. We got 99% removal, but the removal capacity was not very high, particularly compared to an anti-exchange resin, only 1,600 to 2,000 bed volumes. The University of Houston, this was in the same period of time in the 1980s, also did some studies with alumina with the uranium concentration around 120, found 99% removal, but again, very short or a very small capacity, only achieving 2,500 bed volumes. So although alumina, activated alumina, has the designation as a small system, it's compliance technology, its removal capacity is very small. You would have to regenerate it. And currently, I know of no system that is using activated alumina for uranium removal. Okay, I'm going to switch over to reverse osmosis. Once again, some very old data. I was involved in some pilot plant studies back in the 80s down in Florida, treating Florida groundwaters with uranium. We had a pilot system, and an RO pilot system, we operated it according to the manufacturer's specification for the membranes. We evaluated the performance of 4 membranes: the Film Tech, the Dow, the DuPont, the Hydronautics. You can see the percent recoveries for each one of these membranes, a low of 10 up to as high as 59. The feed water uranium varied from a low of 154 up to almost as high as 700, and these were groundwaters we found in Florida. We ran short-term tests anywhere from 4 to 13 days. Number of samples collected ranged from 7 to 22. And we got very good percent rejections, 99%, in 3 cases, 98% with 1 membrane. And I need to remind you, these were membranes that were developed in the 80s, and we know that membrane technology has improved substantially since then. So if these old membranes have this capability of removing a very high percentage of uranium, we know that the newer, more well-developed membranes can achieve even better than this. The last system I want to talk about is point-of-use RO. Again, I'm drawing from an arsenic demonstration project that was out in Idaho. This system focused on point-of-use RO. There were 9 homes with a community water supply. They had between 30 and 50 people in these 9 homes. Several of them had water softeners because of the hard groundwater. We installed water softeners in those systems that did not have them. So all 9 systems had a point of entry water softener, softened the water, and then this was followed with a point of use RO system under the sink. The well water at this site had an arsenic concentration of around 58 micrograms per liter. It had nitrate, and this is as in 11 milligrams per liter, just slightly over the MCL. Uranium was right at the MCL, but it would go up would be below 30 most of the time, but on occasion it would get up above 30 microgram per liter, the MCL, and then vanadium. So you're getting some bonus information with this discussion of this project. Here is the breakthrough curves or the removal curves for the arsenic data. We sampled these systems monthly for a year. As you can see, the water coming into the system had arsenic concentration between around 50 up to as high as 60. As it goes through the water softener, no arsenic is removed because of the anion. We know softeners only remove cations. The home RO system dropped the arsenic level to around detectable limits, in this case of around 1 microgram per liter. And as you would expect, then the reject water was above the influent water. This is the data for the removal of nitrate. Once again, you can see good nitrate removal by the RO system. Here is the curve for uranium. Once again, very good removal by the home RO unit. The uranium coming out of the system for this whole year was less than 1. And then finally, vanadium, which is, I think, listed in the current CCL list. There was interest at that time to see how well the RO system would perform. And once again, as you would expect, the RO system removed vanadium very high percent with the amount being less than 1. Okay, that covers my quick comments on treatment technology, and I know my time is getting short here, so I just have a few slides on waste disposal. You're going to see this term TMOR, and it has to deal with treating water for natural occurring radionuclides, and it results in residual streams that are classified as technically enhanced natural occurring radioactive materials. And it's defined as natural occurring materials such as rocks, minerals, water, and soil and water with radionuclide concentrations or the potential for exposure to humans or the environment is enhanced as a result of human activity, and human activity means water treatment. Back in the year 2005, there were 13 states that regulated these materials. Now, whether there are more states that do this, I'm not up to date on that, but I know back in the year 2005, there were states that had regulations addressing TMOR. Some background information regarding, again, waste disposal. There is a low-level radioactive waste policy act, and it defines low-level radioactive waste that includes what they call radioactive source material. The NCR considers uranium and thorium as source material, but not radium, and it regulates uranium and thorium as source material. And we had a speaker from NCR at one of our small systems workshops several years ago, and at that time he indicated that they were really trying to exclude uranium from their oversight, but he indicated it would take an act of Congress, and he said it would probably take a long time for that to happen. They mentioned source material. They have a, in their regulation, it mentions source material is of an unimportant quantity and therefore exempt from the NCR or the NRC regulations if the uranium or the thorium makes up less than 0.05% by weight. And this is approximately 335 micrograms or picocuries per gram for natural uranium. And this limit applies to both the solid and the liquid residuals. And currently the regulation of this material, this is the unimportant quantity, is up to the states since it's not regulated by the NRC or the local water treatment plant or maybe the sewer authority or even the wastewater disposal facility. At the bottom of this slide I've mentioned or I show a Office of Water document, which is a very good resource if you're interested in learning more about the management of radioactive residuals. A few comments about waste disposal. This slide shows the technology and then the type of waste that are produced, breaking it down between liquid and solid waste. The anion exchange, if it's regenerated, the primary source is brine. That's why I've listed in red. If it's used on a throwaway basis, the primary problem for waste disposal is the exhausted resin. For active alumina, you would probably have to use this on a regenerated basis, and the concern would be disposal of the caustic solution. As I indicated, I'm not aware of anyone using activated alumina. And then finally, with reverse osmosis, the concern is the liquid waste, which is the reject water. The options for waste disposal, if it's a regenerated anion exchange system, produces the brine. Generally, if it's at all possible, you want to go directly to a sewer. I know some small systems that I worked with years ago that they actually hauled it off to a wastewater treatment plant. If it's a one-time use, throwaway resin, if you do the analysis of the resin and it's less than 0.05% uranium and it's listed as the unimportant quantity, it can go to a normal landfill in the state if the landfill or if the state will permit it. If it's above this, then it becomes a greater problem, and generally these systems will hire some licensed hauler to haul away to a radioactive waste facility. For RO system, central treatment, I would say that you have reject water to dispose of, and if you don't have a sewer, very likely you're not going to go with an RO system. For point of use, you can go directly to a sewer if that's possible, or a septic tank system. The bottom line is you really need to check with your state or your local wastewater treatment plant or some sewer authority or the solid waste disposal facility to find out whether they will accept the waste from your system. I might mention that in the two arsenic demonstration projects, which we had arsenic and uranium, the system out in California that had the modified resin, we had to terminate its operation because of arsenic breakthrough. We analyzed the resin. The uranium was 0.03%, so it was below the exempt material. And based upon the NRC regulations, that it could be hauled off to a local landfill. However, the media had to be analyzed to see whether it would pass the TCLP test for arsenic. It did pass, but it did not pass the California TTLC limit, and therefore the media, based upon the California criteria, was considered a hazardous waste. They have difficulty finding someone in the area to handle this, and then ultimately what they did is they hauled this off to a facility in Idaho, which was permitted for disposing of industrial waste, hazardous waste, and low-level radioactive waste. And they hired a licensed hauler to dispose of it. And then with the other projects where we had the point of entry softener and the point of use in these homes, both of the waste, the brine waste from the softener and the RO reject water, was discharged to their home septic tank system, which the impression I got was acceptable by the state at that time. And this is my last slide before I get to the summary. A comment about the regenerated anion exchange systems, and it produces brine waste. And what happens is when you regenerate, you're producing slugs of brine, and in many cases the wastewater treatment plant or the state will not allow this to go directly to the wastewater treatment plant. So there's a couple of possibilities of getting around this problem. One is to store the brine waste on an on-site container or tank and then bleed the brine waste into the sewer over a period of days and sites. So instead of getting slugs, they're getting just small quantities of uranium. And this is generally what's occurred in the past before they put in treatment. And as I said, this is generally acceptable either to the state or the wastewater treatment plant. And many years ago, I worked with a system in California, and this was required by the state. They had 2 tanks of media, and they would regenerate one of these tanks every month. So each tank operated 2 months. At that time, their brine waste went into a below-ground storage tank, and then they would bleed the brine waste into the sewer to the wastewater treatment plant. So this is one possible way of getting around this problem of producing slugs of brine waste that must be disposed of. Okay, in summary, anion exchange, activated alumina RO, point of use RO are all small systems compliance technology for uranium removal. Of the SSC technology, I found that anion exchange is probably the most commonly used treatment technique. And some of these anion exchange resins have very high removal capacity, over 300,000 bed volumes, as high as 400,000 bed volumes. These resins can be operated in a regenerated mode or a one-time use mode. In talking with Jerry Lowry, who's probably installed over 30 systems, he said years ago most of them were operated in a regenerated mode. And for these very small systems, he said more recently almost everyone has gone to using the anion exchange resins on a throwaway basis. If you're using it on a regeneration mode, you almost have direct access to a sewer, unless you've got a very small systems where you could haul the waste off to a wastewater treatment plant. But very likely most of the very small systems are going to operate these on a one-time use basis. And then finally, RO and POU RO are very effective for uranium removal as well as other contaminants that the water utility may be experiencing. But they must have a good option for reject water disposal. So with this, I know I've used up my time, and I think we're right down to the 1 hour, and I guess it's time for question time.
Okay, great. Thanks, Tom, and thanks, Sam, for your great talks. And before we go to questions, we realize it's 3 o'clock, so if you have to go off, we acknowledge that. And our next webinar will be on February 23rd on strontium and nitrate, and then March's webinar will be on March 29th for point of use, point of entry type treatment technologies. So at this point, we're going to go through some questions that were sent in. If you have additional questions, go to the question box and put them in. The first question will be for Sam. So if a system installed a new well in 2008 and took baseline samples, including radionuclides, but does not use the well until 2016, can we accept the 2008 samples, or do they need to collect 4 quarterly samples now? Sam, are you there?
Oh, can you hear me now?
Ah, yes, we can. Thanks.
Okay, great. Yeah, so the question, I think I would say that those results would be acceptable if that baseline was performed at that specific well. What I would say is that I think the state's approval or review on, on this issue would be very important. There's a few things that they would have to keep in mind. I think one of the, the most important one would be what were the results of that initial monitoring on that specific well, because that would determine the subsequent monitoring scheme. But I don't see any reason why that data would not be valid to make determinations for initial monitoring. I think the other item to give into consideration would be if there are any other wells in the vicinity of that well that we're talking about, and I think it would also be important to know what's the baseline of those other wells that might be in the vicinity, and those might be also considered as being representative of what's going on that well. So in short, I think I don't see any reason why those shouldn't be accepted. But again, the state will have to decide that.
Okay, great. Thanks, Sam. Here's another one. If a water system's gross alpha is below the MCL, but the uranium is above the MCL, even when the gross alpha result is below 15 picocuries per liter, can we still require uranium monitoring not based on the gross alpha result?
Yes, can you hear me?
Yes.
Yes, okay. Yes, I think this is a good question just to clarify, because this is a point of confusion sometimes. So when we need to make the distinction between gross alpha and what we call net alpha. So in the presentation, when we were talking about substituting gross alpha, when we use that term gross alpha in this issue about substitution, we mean gross alpha in that it includes everything. Includes everything. So uranium would be included in that gross alpha definition. So in short, it's not possible to get a result of gross alpha that it's below 15 and uranium would be above 30. Now the issue and the confusion is between the term gross alpha and when we talk about net alpha. And net alpha is the value that might be used for determination of compliance, and that is the number that you would get the gross alpha, and then you would subtract uranium and radon. So when you subtract uranium and radon, what you end up with is net alpha, and that net alpha, the MCL for that, it's when, you know, what we talk about, that 15 picocuries per liter. So I hope that this clears that doubt a little bit, but I think this is the issue. It's that distinction between gross alpha and net alpha. But for the opportunity of systems to make substitutions, when we talk about that, it's really gross alpha, and that would include everything.
Okay, great. Thanks, Sam. Here's one for Tom Sorg. What other pollutants are likely to be in the brine?
I assume we're talking about the brine from an anion-exchange resin. So any contaminant that this anion-exchange resin would remove, such as arsenic, nitrate, as we showed, even vanadium, once it's regenerated, all those contaminants would be released from the resin and occur in the brine waste. So anything that the anion exchange system remove, you'll find in the brine waste.
Okay, and here's a question on pretreatment. What sort of pretreatment is needed for anion exchange in RO systems?
Your main concern is fouling either of the anion resin or the membrane. So if you do have maybe an iron and manganese problem, you would need to investigate the potential for fouling of that material, and that material would either potentially have to be removed beforehand or handled in such a way that it was not going to foul the resin or the membrane.
Okay, and here's a definition of terms. I've never heard the term BV, bed volume, before. Can you explain what that is?
Okay, a bed volume refers to the volume of the resin. So if you have 1 cubic feet of resin, the bed volume is 1 cubic foot. So it refers to the volume of the material itself. And it's a common way to report how many bed volumes it can treat. And it's based upon, as I said, the volume of the media. So it's sort of a normalized way of presenting the data. So if you have 10 cubic feet or 20 cubic feet and it can remove 10 or 400,000 bed volumes, you just multiply that times the quantity of the material. Okay. So it's a way of normalizing its removal capacity.
Okay, thank you, Tom. This was a question for Sam. When does EPA consider an exceedance of uranium MCL, 30 micrograms per liter, a violation of the Safe Drinking Water Act? Would it be 1 year of quarterly samples greater than 30 micrograms per liter? 5 years, 10 years? When does enforcement actions begin for multiple exceedances?
Okay, hi, this is Sam Hernandez. Okay, so this question, when first, who's going to determine violation or exceedance, or exceed what would be like the state that is enforcing the regulation? But in short, I think this goes back to that example that I was mentioning about. It depends on how the state determines how compliance would be determined within the standardized monitoring framework. So in reality, let's say that a system completed initial monitoring and they were in compliance of the MCL, and the monitoring scheme would call that system to sample every 3 years. So it's possible that a state decides that the next sampling that has to occur, it's just once every 3 years. So if in that sample the system comes up above the MCL, that would be an automatic violation of the MCL. There's also a possibility that that state decides that compliance would be determined with multiple sample events. Let's say, for example, like 4 quarterly samples, or a state could even say it's going to be 2 samples in 1 year to determine compliance. So I would say that it depends on what the state determines for compliance, but I just wanted to add that if a system has to monitor within their standardized monitoring framework, and that result comes up above the MCL, that's an automatic violation of the regulation.
Okay, thank you, Sam. Here's a question for Tom. Were the point-of-use systems NSF ANSI 58 certified for performance for uranium removal? Which point-of-use systems were tested?
I'm on the point-of-use committee for NSF, and currently they do not have a testing protocol developed for that. It has come up at a number of the meetings, and I guess they just haven't gotten enough pressure to go ahead and develop a testing protocol for uranium. So to my knowledge, there are no systems that are listed by NSF for uranium removal.
Okay. Here's a question for Sam. So is Sam saying that a uranium concentration in drinking water should never be reported higher than gross alpha? A clarifying question.
Okay, yeah, I don't quite understand this question very well, but I'll try to clarify this issue. There's 2 separate things, okay? So one is the MCL for gross alpha, and that MCL says that it should be below 15, excluding radon and uranium. So that's one thing. The other thing is the regulation for uranium. So, and again, this is the issue with the terms of how you calculate that gross alpha, how you are able to do the substitution of gross alpha for uranium. But again, just to clarify, the gross alpha regulation, which is 15 picocuries, excluding radon and uranium, it's 15. Now, if you wanna substitute your results for gross alpha, and that's gross alpha in the way that it includes everything that we earlier said that we could substitute that for uranium, you have to meet the condition that it's below 15. So again, I think the confusion here is about the terminology that EPA use, and we recognize that this is a little bit confusing, but we decided to keep the terminology that way because since 1976, that was the way that we have been using this. But again, we understand that this might cause some confusion. But the gross alpha MCL, it's 15, excluding uranium and radon. And depending on your results for gross alpha, including everything, you could substitute that result for uranium as long as you're below 15 picocuries per liter. So I don't know if that clarified that a little bit or make it more complicated, but I think that's the response.
All right, thanks, Sam. I think that helps. Here's a question for Tom Sorg. If present above the MCL, what are some treatment techniques that will address very high levels of radionuclides present in water?
I assume that we're talking about uranium rather than some of the other rads. If you recall, when I went through my slides, we did work with concentrations up to almost 700 micrograms per liter. And with RO, we got over 99% removal. And I think even your ion exchange resins are very effective for high concentrations of uranium. Their capacity for removal is going to be dependent upon the concentrations, but maybe more dependent upon the sulfate level. So I think it can remove it, but its removal capacity by ion exchange would be less than if you had, much lower levels and waters with that are low in sulfate.
Okay. And here's a question about Z-light treatment. So this was a very interesting presentation. I was very curious if you are familiar with Z-light treatment for uranium removal.
I've got to admit that I've not done any work with those products, and I've not seen much information in the literature, so I am not familiar with it.
Okay. And this is a question about discharging reject water. So for the point of use RO systems discharging reject water to a septic system, is there a potential for creating concentrated radioactive waste, since many homeowners do not pump out their septic systems on an annual basis?
Again, this would be my personal opinion. Uranium is very soluble, and unless it would attach itself to some of the solids in the septic tank, it would not remain in the septic tank. It would go out into the drain field, into the groundwater. And I suspect that this is what would happen. I'm not convinced there are the type of solids in the septic tank system that would absorb or hold on to the uranium. When they're pumping out the system, of course, they're going to have the solids as well as some of the liquids. But being alpha emitters, there shouldn't be any problem with the operator handling it. And personally, I don't think it would be a real problem.
Okay, here's a question for Sam. I think they mean, where can they go? Can a person take and have samples tested if suspicious of contamination? So I think where would you go for analysis, perhaps?
Yes, this is Sam. I would say that well, first the radionuclide rule, this applies only to community water system, and that's a very specific definition of how you determine that. But for private owners or people that might be concerned about the quality of their water in a private well, there are ways to sample the water. I think the best way to do that, I would suggest that if there's a water system that is close by, that they can call and request for information about what laboratories they use, I think that would be a good place to start. If not, I would suggest that they get in contact with the state, specifically with the office that has authority for implementation of CIDWA, and I'm sure they're in a better position to point them to where they might be able to get a laboratory that might be able to perform the monitoring for a private well. I think that would be the best place to go and seek information for that specific location.
Okay, great. Thanks, Sam. Here's one for Tom. Regarding pretreatment, do some wells have no pretreatment requirements? Or are some waters available to treat? I believe the previous question was anion exchange or RO treatment, pretreatment question. And this one is, are there some waters that don't need pretreatment?
The waters that would not need pretreatment would be any of the waters that would have substances that are, going to, well, let's say the ones that would need pretreatment are those that have substances that would potentially foul the material. So as I said before, particularly iron and manganese would be the main concern. I've gotten the impression, talking with Jerry Lowry, that most of these systems have not had any serious problems with pretreatment. As I said, particularly if it's low on iron and manganese. If it's high, then you do have to do some pretreatment.
Okay. Regarding the disposal of point-of-use systems, so what is the recommendation for disposal of point-of-use RO system for a homeowner? Disposal of the system itself.
Disposal of the system itself, I think it can be handled in a normal way. I would suspect that the membrane may have some uranium on it, but I can't say I've actually collected samples of the membrane to determine how much. The impression I've had is, again, because it's an alpha emitter and the concentrations are rather low, that it's not a major problem in getting rid of the membranes.
And is there any research on radium or radionuclide levels adhering to deposits on distribution system piping?
We did some work many years ago. I sponsored a project with Richard Valentine at the University of Iowa, and we looked at radium being deposited in the solids in the distribution system, and we did see uranium being absorbed onto some of the solids in these pipes. At the time, we did not do any work with uranium because the waters, I know in Iowa, the biggest problem was not uranium, it was radium. So I think, yes, there is the potential for radium to be included in the solids that you'll find in these distribution pipes if the groundwater has radium and it's going out into the system.
Okay, and we've got a couple questions about radon treatment. So and if I could summarize them together, it would essentially, could you speak briefly about treating radon in drinking water?
It's not uncommon to find radon along with uranium or radium. We did work many years ago on radon treatment, and the two technologies that I think have been used, number one is aeration. Radon is a gas, and I've seen systems by Jerry Lowry treating radon removal. In almost all cases, it's aeration treatment. We also know that carbon will remove radon, but then you have a product to get to dispose of. So I would say that aeration is probably the technology that most utilities would use if they have a radon problem.
Okay, and here's a quick question. I think you covered it on your speciation plot, but does uranium dissolve in water?
Yes, that's the problem. It's very reactive, and it's a dissolved substance.
Okay, great. Well, I think we've gone through many of the questions, and I think we're ready to wrap it up today. So thank you so much for Sam and Tom for giving these presentations, and thank you for listening to our webinar. Again, next month we have our webinar on February 23rd on strontium and nitrate, and then in March it's point of entry on March 29th. You'll see more on the website as we start putting together this webinar series for this year. So thank you so much for your attendance, and I hope to see you next month.